Good evening and welcome back to Vegas October 1 Sounds. Tonight we're going to do some scribbling on my screen here, and what I'm going to do is talk a little bit more about the nature of the supersonic shockwave front. And I need to do this because, as I've explained in several videos now, the wavefront generated by a supersonic projectile and the conic shape of it have many implications for when people hear the crack. And tonight I'm going to go over one aspect, one situation that I think is going to be both interesting and revealing to those that haven't really given it great consideration. So let's start off with what I've generally been talking about. I've generally been talking about how when a bullet is initiated from a firearm, and it travels out towards wherever it's going to travel. The bullet being traveling faster than the speed of sound creates a series of shock waves that cumulatively have the effect of producing a cone-shaped like wavefront with its head at the bullet and its tail obviously trailing behind it, much like when a jet is supersonic. It has a similar phenomenon. Sometimes you can actually see the cone when it was right there at the transonic speeds. So anyway, in this little image we have a bullet traveling from left to right, and we have the cone trailing behind it. And now the question becomes, and as I've sort of discussed in other videos, if we have a bullet traveling parallel to the ground, then when the cone intercepts the ground, it's going to do so in a way that is not making straight lines, but it's going to make parabolic or hyperbolic lines depending on the angle of approach and everything on the ground. That is, not everybody who has the same X or Y coordinate will hear the sound at the same time, because those who are directly underneath the bullet will hear it sooner than those who are somewhat removed from the bullet path, either laterally or cross distance. So in this side view, we've talked a lot about the shape of the cone, and the shape of the cone is regulated by the ratio of the bullet speed, which I'll call V, divided by the speed of sound. And as I've explained several times, the speed of sound, of course, is dependent upon temperature, moisture, humidity, elevation, all those sort of things. But the temperature is the biggest one. And if you'll know the temperature, we can get a good approximation to what the speed of sound will be. And that ratio of the bullet speed to the speed of sound produces a cone, and the angle as measured from the trajectory path to the leading edge of the cone, which we'll use the Greek letter, let's just call it alpha in this case, is what we call the Mach angle. Okay, and the Mach angle then in degrees is easily determined by simply taking the inverse sine of the ratio of, well, actually, let's make it easier. If the Mach number is equal to the ratio of the bullet over the speed of sound, then the angle is given by the inverse sine of 1 over m. Now, you don't really need to know any of these formulas because I'm going to, just tell you. So for Mach 3, the angle is probably, and it just does, I don't have it off the top of my head, somewhere on the order of 19 to 23 degrees, let's say. For Mach 2, it's probably approaching 30-some degrees. For Mach 1, it's 90 degrees. So as this bullet slows down, this cone shape becomes broader and broader. Now that's some of the basics of the cone. And the cone is being created at the speed of sound, at the tip of the cone, but when it propagates, and once the bullet passes, it's just a normal sound, and it propagates at the speed of sound away from the trajectory of the bullet at an angle, and that angle is once again the Mach angle. So if I erase on this picture all the equations and everything, because I really just want to talk graphically about what's happening, then this wave, the leading edge of this cone in all directions, will propagate. For every increment of time, it'll move further and further away from where it was. Now, in this case, you notice I'm not drawing the lines down to the bullet path, but they would at some point go out there down closer and closer, much like this, and form a complete line. So, and the direction of travel of that leading edge of the cone is perpendicular to the leading edge of the cone. So, and it occurs on both sides, of course, because the cone is symmetrical about the bullet path. And so you have basically a cone that gets broader and broader, and these wave fronts that are moving both away from the bullet path and yet forward in the same direction as the bullet path. So what happens if the bullet stops? Let's talk about that for a second. I might as well start there because it's an interesting phenomenon. If the bullet stops, then obviously you can no longer generate the cones. So we have a bullet here going left to right, and it's generating this cone, and at some point it hits an object and it stops. And that bullet moving through the air, compressing the gases, is the thing that is fueling the creation of the cone. And so when that stops, the creation of the cone ceases. But the part that was already created remains, and it propagates just as it would have, without hesitation. It propagates out in the same pattern, except that the leading edge now is not being refreshed or regenerated. And so we get these patterns of waves that follow the conic shape but have no head. So it's sort of like cutting the head off something, and you can see down the throat of it, and that's what happens essentially with the cone when the bullet hits something, is that the head is removed, and you can actually sort of visualize it as seeing right through the cone with an empty spot. Now it's not really empty, because sound is sound, and at the edges of what would have been the leading edge of the cone, you get sounds propagating just as though they're little bitty point sources all along here. And so you get something that resembles, and I can't go into the real details of it because it's a complex fluid dynamics problem, but basically you end up with it sort of being a roundish thing in general, but of substantially reduced volume, so that you may actually hear or record a crack in that region, but it's going to be 10, 100, 1,000 times less intense than these big parts here. You see, the big parts of the cone, the leading edge of the cone while the bullet's active, is strong because it's the cumulative effect of many, many waves. To express that, let's draw a simple example. So if back to the model of the spheres, let's do it in great detail. We take a bullet with a boat tail on it, and for those not familiar with bullets, it's basically on the front of it it's a cone, and on the back it's flat, but the flat isn't flat completely. It's got sort of a little dip down on both edges. And then we have the gases, as it pushes through, being compressed at the very front of this, and then they come up around here, and then they have to go back in, is basically what's happening. And the net effect of that continuous operation is the creation of that cone, okay, because they don't go back in immediately. There's some width at which there's very high pressure at the leading edge of the bullet, or leading edge of the cone, and then there's very low pressure at the tail end of the bullet. And there's some actual width to that shock wave that gets created. And actually, there's a lot of fine structure in there. There's multiple shock waves in there because the gases are a fluid, a compressible fluid, that's doing a lot of things. It's like watching a flock of birds when they decide to turn or interact or whatnot. It's a fluid thing. It's not this, you push the end of a stick, hockey stick or something against the puck, and the puck goes flying in a fairly consistent pattern. It's a dynamic, it's a fluid thing. It's, there's a lot of beautiful stuff going on there. But anyway, so once this bullet disappears from the picture, then we essentially get the tail end or the head part of the cone as having no energy to continue. But back to the creation of it, these sounds which have a width, the shock waves has a width, and it's that width that creates the sounds. And how can I put this? Were it not for the next moment in time, you'd have one sound and it would propagate out in a sphere. But because it's a continuous process, each time increment contributes to both the last moment and the next moment. But once the bullet goes away, then you don't have that contribution. So when the bullet goes away, then the edges up front no longer have energy. But it doesn't just affect the front edge, it affects, in a region that is, when the bullet just leaves is right at the front, but overall then that has an impact that affects the strength of the linear portion, the leading edge of the cone. So, how can I rephrase that? I don't know. I don't need to. But anyway, so when the bullet stops, the sonic cone continues, and we get different patterns depending upon how fast it was. But we end up with something that looks like a I'm trying to think of a V, in that there's fairly strong I'm drawing pictures here now of that V. Fairly strong sounds where the leading edge of the cone is, was, or will be, and the perpendicular lines of flow to that, which is the direction of travel on both sides of the once existing bullet, form a V. So even though the bullet stops and you're some distance away from where the bullet stopped, you may encounter still a very strong sonic wavefront shock wave, depending once again upon your position. If you were in the direct path of the bullet, not so much. But if you're, say, 60 degrees out, probably so. And in the picture here, you can see that, there are places where, if I drew all these lines out, there would be a region marked here in yellow that's directly along the old path of the bullet, but between the two portions of the now propagating, without being more creation, cone, with missing a head. So, it's not a one-size-fits-all. You can't model everything with one simple model. You have to take into account the angle of approach, the speed of the bullet, the speed of sound, whether or not it hits something, a whole bunch of criteria. And that brings me to my second point now. And so anyway, I call this a dead bullet scenario, where the bullet is no longer supersonic, and it's not an easy thing to wrap your head around all the times. So let's talk about a more interesting situation, and one that is very relevant to the Vegas. So we understand that we've got a cone that was produced by the supersonic projectile, and we understand it is the shape and size of the cone is dictated by the ratio of the bullet speed to the speed of sound, and it has a width and it gets wider as it slows down, blah blah blah. But in Vegas we have the situation where we don't have a bullet traveling parallel to the Earth. So that cone now has an angle relative to the Earth. And if we draw a picture of, that's the front of the Mandalay Bay on the left-hand side there, and we've got a gun shooting from theoretically an elevated position, but to hit a target down here on the ground, you can't just fire straight out the window because the distance to the target is too short. I mean, yeah, if you're a mile away, you could probably, you'd probably have to elevate it somewhat. So it has to, the firearm has to be essentially aimed down, which changes all the dynamics of the ballistics of the gun. Well, it doesn't change it, it just changes, where it's going to hit and how you adjust your sights and that whole thing, which I question that Paddock even was aware of that phenomena, because if he sat somewhere, let's say he went out to the dump and he zeroed in his gun for 300 yards, and then he came back to the Mandalay Bay and without readjusting his sights shot at something at 300 yards, it's not going to hit it. It's going to go over it or under it, depending upon how he adjusted his sights. But because the bullet is going down, accelerating towards the ground, it takes less time to get the ground, and therefore there's less time for the bullet to, say, drop because of gravity. So because there's less drop, means that when he zeroed in at 300 yards and he now shoots at that a target from an elevated position, then it's most likely the projectile is going to go over the target. Alright, but anyway, let's talk about the cone. So we have the trajectory of the bullet, and it's not going to be really a straight line, but let's just use a straight line for our example here. And we have a cone. Now the cone, let's say, is about 30, let's just use about 30 degrees, and my cone here is a little bit larger, but on the bottom side we'll make 30 degrees here. Okay, so now you see that 30 degree cone created by the projectile, and the gun pointing downwards at somewhere between 20 and 30 degrees. Now the leading edge of that cone on the lower edge begins to become closer and closer to parallel to the ground. What does that mean in terms of when people on the ground will hear the shock wave? Well, in this example where I'm not entirely parallel, people located along the route, shall we say, to the target will hear it sooner than had the gun been fired parallel to the ground. In fact, what we could have is a scenario where at the right angle, at the correct angle, at some angle here, and if I do this, you could end up with a scenario where the cone actually becomes almost parallel to the ground, in which case everybody along the ground will hear the crack at the same time, because it's the leading edge of that cone is what is heard as the crack. Now think about that for a moment. We've got a guy shooting from an elevated position, a guy, who knows who it was really. He's firing down at about 20 to 30 degrees, and the bullet is going Mach 2 to Mach 3, creating a cone that's also 20-30 degrees. And it ends up being that when he fires that bullet, regardless of where the person is located, they hear the crack at something that's almost the same time. Now that's a pretty wild scenario, but it is close to what was happening in Vegas. And I haven't worked out all the numbers, but when I do, I'll plot it up in a graph for you and show you precisely. So I've been giving you these models where the bullet travels parallel to the ground, and we've learned how that works, and we know that the time of arrival of the shock waves is a function of both not only the distance from the shooter but the distance from the bullet path, and we call that downrange and cross range, or distance to the shooter and miss distance. But in this example, you can see that the distance from that shock wave to each of the observers is approximately the same, and therefore once the bullet has gone by, then the shock wave will reach each of the observers at these blue lines at about the same time. Kind of an interesting concept, I would say. Plus, as the bullet's traveling, of course, this cone is getting wider. So even if it didn't start out at 30 degrees, let's say it started out at 23 because it's traveling more than Mach 3. And while it's not parallel to the Earth to begin with, the cone, the leading edge of the cone, it may become parallel at some point, creating a region on the ground for 100 feet or so, where everybody in that 100-foot radius will hear the crack at the same time, even though they're not at the same location downrange. So the dynamics of these supersonic cracks are more than just non-intuitive. They're dynamic, and they're complicated. So this is just one scenario, and this is close to some of the effects that we see in the times of arrivals of the supersonic crack. Now, before I've explained that both the cross distance and the downrange distance have a big impact, and you cannot tell. Well, let's just back up a minute, and I know I'm talking kind of fast here. If you were in that 100-foot region that I just talked about, and you were to measure in absolute time the times of arrivals, then if the bullet arrived at the first observer at time 1, then it would also be arriving at observer 2, 3, and 4 at time 1. So from that, you could not ask a question like, which direction is the bullet coming from, based upon the time of arrivals, because they're all at the same time. Now, you could logically ascertain that if that's true, then the bullet, or that the sounds that you hear must be coming parallel to all the observers. And from that, you could draw this inference, which would be an accurate inference, namely that the cone was such, and the bullet trajectory is such that the cone was parallel to those observers. Parallel from an elevated standpoint, not from an XY ground plane sense. So, now that's not to say that everybody a few feet away in the cross range direction would hear it, because they won't, because this example applies for people directly under the bullet path or close to it, even though the bullet is overhead. So just one more, I call them corner cases, where strange things happens, but these corner cases give us great insight into the nature of things, because it's the corner cases like Oasis Apartments where the lag is very small, even though it's at a great distance from the source of the where the shooter is located, basically, that gives us the realization that the time of arrival of the shock wave at that location basically is the same as the time of arrival as the muzzle, because the shock wave we hear had to have been created at very close to the muzzle to have reached Oasis in a way that is consistent with the physics of gunshot acoustics. Whereas, let's say Oasis was 1,200 feet away. If you took a 1,200 foot away position directly along the line of travel of the bullet, then you're talking a lag which is large. Oasis apartment is, let's say, 40 milliseconds, and somewhere along the line of the bullet at 1,200 feet may actually, if the bullet made it that far, might be on the order of half a second. So the same downrange distance, different lags because of the cross range distance. But the corner case, is Oasis because the angle between the bullet trajectory and the observer, namely Oasis Apartments recording, is so great. In fact, talking about that, in most real scenarios, once this angle between the bullet path and the cross range angle as measured from the bullet trajectory to the observer reaches more than about 49 degrees, there's a whole different scenario that takes place, and basically the sound becomes a point source close to the supersonic crack or shock wave can be modeled as a point source very close to the muzzle of the gun, because the propagation paths are nearly identical. And of course, the other corner case is directly along the bullet path, and that corner case yields very simple examples, very close to what Health Ranger was trying to say, but he couldn't say it in a way which, was accurate for the observations he made, because, he was trying to say that change the lag and you change your location, and that location is a function of only the distance to the shooter, which is not true. Alright, so I wanted to bring out that corner case, and it's food for thought, because a lot of times these corner cases stop us from making rash statements that can easily be shown to not be true. And if we go back and we look at, let's erase part of this scenario, and let's say we have that, and then we pick some shooting locations which are cross-distanced different. In other words, we'll have one path, one observer close to the bullet trajectory. Now, in this case, this can't be the case because this is a side view and one person would have to be elevated. But if you were to look at it as a top perspective with the same scenario, we can apply this. But let's just take this for a case. If we had one observer who was a foot above the trajectory of the bullet and one observer who was higher than the source of the bullet initially, it is possible that they could both receive, hear and record the shock wave at the same time, because the line drawn between those two observers is parallel to the leading edge of the shock wave. So, there's a lot of ways of looking at this that can yield useful information, and I think this is one thing. How parallel are you to the leading edge of the shock wave? And if there's 2 points which are in a line parallel to the leading edge of the shock wave, then they're both going to hear that shock wave at the same time. That's just another way of phrasing that, the shockwave arrival time was a function of downrange distance and cross-range distance, and it's a combination of both those, and for those points the sum total of those things turns out to be identical or close to it. Alright, so let me talk about a subject which I'm going to be addressing very, very soon, as soon as I have all my graphs and charts and numbers worked out and verified. A lot of times what systems for gunshot detection rely upon having multiple sensors synchronized very closely and accurately, so that when the sound hits these sensors, you can tell which sensor the sound arrived at first. And from that arrival time, you can get a real good indication of which direction the sound is coming from. So let's draw a 3-sensor system, and I'm just going to draw the sensor locations randomly here. Okay, let's say you have a helmet, for example, and you put 3 sensors on it. And you have each of these sensors synchronized. Then, and there's a sound emanating from somewhere, in this case the upper left hand side of my screen, and it propagates out here, and you can see from this that it's going to, oh, I forgot to label them. Let's call this one A, this one B, and this one C. Now in this scenario you can see that that sound is approaching sensor A, and it will be recorded first, and then it'll continue to propagate, and it'll reach sensor B, and finally it'll reach sensor C. So from that we can ascertain that the general direction of the sound is towards that arrow I just drew, which is, you know, gonna be a reasonably good approximation to where the sound is coming from. And notice I'm not necessarily talking about any muzzle or any sonic. I'm just talking about a sound in general. It could be the leading edge of a cone. It could be the leading edge of the muzzle blast. It could be somebody talking. It could be anything. But from those 3 sensors, then, with the precisely aligned clocks, we can make real good approximations to what the direction is coming from. Now, once again, you know, there are situations in which this configuration will fail because it takes a minimum of 3 points and to give a real good indication of direction. So if the wave, let's do another wave, let's do a red one. If the wave is coming from a direction where, you know, 2 of those sensors are hit at the same time, then with just 2 sensors you would not be able to tell where the shock wave was coming from. The only thing you'd know is that it was either coming from the top or coming from the bottom, because, you know, there's 2 different ways at which that could occur. So to resolve which direction it's coming from, you have to have this 3rd point, and then that 3rd point will give you the which side of the sensor array that the sound was coming from. Well, Vegas isn't such a clean proposition. We don't have synchronized clocks, and even when we think we do, i.e. the patrolman body cameras, we find out that they're not that accurate, and they're not necessarily synchronized. You know, some are off by tens of seconds. Some skip seconds in the video. Who's to say what the real accuracy of them is? So, one way to attempt to address that problem, because we really would like to have synchronized time so that we can say with some degree of certainty that a sound is arriving at a recording device at a particular time, which can be counted on at the next video as the same or different time. So what we do to, you know, achieve that, or to simulate that phenomena, is to synchronize videos together. So we have 2 videos, let's say. Let's say video A, video B, and you pick your favorite scene. So for example, let's say we pick the Raymond Page, and, you know, and they're walking, and we got the sidewalk scene, and the cars over here to the right on the boulevard, and then over somewhere up in here is the Mandalay Bay. And then we have let's just pick the Oasis. I'm really fond of the Oasis Hotel. So somewhere then we have the Oasis recording, and it too has an image of the Mandalay Bay just really far away. So what we do is we look for common events in both of them, and then we align those events. Now, if you align the sounds, then you have to contend with the delay or the speed of sound between the source of the sound and the arrival of it, some milliseconds in doing, at the video. So rather than trying to synchronize the videos with the sound, because it's not obviously the propagation delay of the sound to the recording is going to be different for each recording unless they're at the same distance from the source of the sound. So what we do is we find events that are in the video or light-based to both of them, because light speed is so fast that the propagation delay is essentially zero for our purposes. What I've done is chosen the sign or the marquee out in front of the Mandalay Bay. And so I look for different transitions on that sign that occur that I can then synchronize these two videos. And generally what I'm looking for on the marquee are transitions from light to dark or dark to light. And if you've ever looked at that marquee, you notice that it has some pretty regular changes. So you do an approximate alignment with the sound on this thing, because sound is easy to align them with. Well, it depends upon what tool you're using. But anyway, let's line these up. So let's pick a transition from dark to light or light to dark, and we'll find it in both videos, and then we'll record that time, and we'll synchronize the videos, and you can do it in your favorite movie maker or any other thing as long as they're synchronized. And then you can take the combined sound of both videos if you choose, and you can look at when sound events occur. And because you've aligned them with the light, those sounds will be separated in time proportional to the propagation delay from the source. So Oasis, and let's take most of the volleys. So Oasis, if it's 1,100 feet away from the hotel, that's an if, that's not an exact number, then you have a 1 second delay between when the sound occurs and when it gets recorded on the tape. And for Raymond Page, it's probably more like, depending upon where he's at, but let's say he's at the very top of the boulevard near that exit gate. What is it, 2A? Yeah, 2A. Then it's probably more like 0.4, let's call it 0.5. Alright, so when we align these two videos with the light, then there'll be a 0.5 second gap between those two sounds. And so now, using that gap and several measurements, you can start to determine what the distance is to the source of the sound. So the problem occurs in that how accurate is that measurement? Namely, in this case we're dealing with 0.5 distance because Oasis is quite far away. But if rather than having this be Oasis, this were there's a guy standing on a trailer or a bathroom right next to the VIP tents on the west side. I call it a cross. So the across one. So he's just a little further more into the venue than the cops on the corner. Or we could even use let's use cops. Or no, I'm going to use a cross because they're roaded out here. So across, you got this guy. He's standing on the top of that trailer, and and the cops are telling him to get down and blah blah blah. And he is not 1,100 feet away. In fact, he's much closer than Raymond Page. So his propagation delay time for a sound from its source, namely, let's presume room 135, would probably be more on the order of 0.2. So in this case, we're going to have a delta between those two recording events of 0.3. All right. So let's take that. When we aligned these frames, and now this is all presuming, of course, that Across and Oasis and Ray all have video events which are common, because there are videos which have no video events in common. One of my favorite ones is what I call Under, which is recorded right in front of the stage or slightly under it in the middle. and there's no video events common to it with any other video that I can find. So in that case then, by using the synchronization approach, we lose the ability to tell with any certainty what time the events occurred using these techniques. But anyway, let's get back to the accuracy. So presuming that we can find videos that have common events and that we can successfully locate these common events, which takes quite a bit of time, and I'll get to that in a minute. Then what we can do is measure the gap between them, and then compare that to other things and calculate distances and But what I want to talk about is the accuracy. We have we have frames in our videos, and these frames occur once every 30th of a second, because typically, and don't nail me for not being exactly 29.7 something frames per second, but let's say 30 frames per second. Then we'll record one frame every 30th of a second, which is about 33 milliseconds. Okay. So if an event occurred such that it was recorded in frame 5 over here, we don't really know within that 33 milliseconds where it occurs. It's just frame 5. It's, whatever the last time was, plus or minus 33 milliseconds. And over here we could have the same thing, frame 25, because they don't start at the same time, and it too would be plus or minus 33 milliseconds. Okay, well, 33 milliseconds might seem like a small number for your average everyday thing, but for trying to make precise measurements with sound, which occurs at the sub-millisecond level, and then coming up with an answer that's precise, kind of iffy, dodgy, sketchy, whatnot. So what you end up doing is for every frame that you're off, you get, at the speed of sound, roughly 30 to 50 feet in accuracy in your measurements, depending upon the nature of the calculations you're making. So if you make a 2-frame error, then you're already off 100 feet. And believe me, a 2-frame error is not hard to do. For example, if we go back to the Oasis recording, and the Mandalay Bay is basically just a little blip in that recording. And yeah, you can blow it up as much as you want, but the marquee is almost perpendicular to our line of sight. So there's very little visible portion of the marquee. So all you really do is seeing changes in color of light and changes of intensity in light. And because we are much further away, say, than the Across or the Raymond Page video, which are perpendicular to the sign, so you see them, you see everything on it, then the Oasis, the light having spread from the sign out to Oasis is spread over a much larger distance than either the Raymond Page or the guy on the, I think it was a bathroom there by the VIP tent. The number of photons, if you want to look at it that way, hitting the camera is far less per frame than the other two. So if there's a fixed sensitivity to the CMOS devices doing the recording of the light, and there's a lot less light hitting, then there's a high probability that for low intensity light things, you're going to record either you're going to record a darker frame than what you would if you were closer up. So that means that these regions of darkness on the marquee are possibly on the Oasis recording off by 1, 2, or even 3 frames. So what I do to try to get around that is look for transitions which go in one frame from very, very dark to very, very light, or vice versa. But the marquee wasn't put there just to help me do this, and half or more of all the transitions take 1, 2, or 3 frames if you're close up, but out there at the Oasis Motel, or Oasis Apartments, excuse me, because there is an Oasis Hotel, it's a little longer. And so you have to be very, very careful in doing that. But anyway, so if I'm off by 3 frames, then we're talking about 100 milliseconds, which represents 100 to 150 feet in terms of the speed of sound. And that's why a lot of times you'll see my estimates qualified with, hey, it's, room 135 plus or minus 150 or 200 feet. Because the nature of the synchronization, or the nature of determining the location of the video recording, is such that the inaccuracy becomes a very dominant factor. Now, well, wait a minute, Richard, wait a minute. You've produced 50 or more videos now, and you've told us you can tell when things are moving even as little as 1 foot. That's true. But that's because I'm using the muzzle blasts, and those muzzle blasts can be measured down to the sub-millisecond level. So I can produce and have, and you've seen it many times, an entire timeline based upon muzzle blast recordings that say, if everybody was located at the same position, this is the time that event occurred in the video. And those are accurate down to, as close as I can get it in many cases, and sometimes I'm sloppy and it's only a millisecond accurate, or sometimes even way sloppier and it's 2 or 3 milliseconds off. But that, even at 3 milliseconds, error in measurement is not going to produce 100-foot inaccuracy in my final outcome. It might produce 10 or maybe even 20, which is perfectly acceptable. So you have to be careful in these inaccuracies. And I'm going to be presenting a couple videos on establishing a timeline with this method, establishing a timeline by using the alignment of the muzzles, and I'm going to explain in great detail the advantages and the disadvantages of all of them. So now we get into a little bit more theoretical, and so the astute observer will say, well, wait a minute. People make devices that detect the shooting location of the shooter all the time. They do, but they have these nice little physical devices which they know precisely how far apart all the sensors are, and they know precisely what the timing is because they're synchronized devices. Okay, so in that case, I can't compete with that. Nobody can compete with that. You say, well, yeah, wait a minute, Richard, aren't there ways of overcoming that? Oh, yeah, there are. That is, we don't need to have absolute time to make some real good calculations. We can use these relative times, just the gap, without knowing what actual time it occurred. But when we get lots of measurements and lots of calculations, it becomes, the nature of the algorithms becomes extremely complex, and their solutions become extremely complex, and you have to be a bit of a mathematician to have any faith that what you're doing is correct. And for me, not being a professional mathematician, I have to approach it 5 different ways and make sure all the things come out the same before I even trust myself. So that's what will be coming up in the next couple of videos. But I wanted to bring to light, the fact that if getting back to the thing which I'm beating as a dead horse, which is the supersonic crack, the conic wavefront thing, is that there are scenarios real in Vegas that evening, because there are shots which are fired from an elevated position where the leading edge of the cone approximated a parallel path to the ground, and therefore there were scenarios where the shock wave actually was heard and recorded approximately at the same time for people, quite a ways apart. And that's a counterintuitive thing. So once again, this is another example of why the supersonic cracks were so confusing to people, because they just aren't intuitive at all. Alright, well, that's enough talking about all these technical things, and we'll catch you in the next one.